functional group carboxylic acid, also written this way or this way. All of these are carboxylic acids. So mainly you have a C double bond OOH connected to the one of the carbons. The R, it could be anything: benzene, alkane, cyclohexane, methane, methyl, ethyl, you name it. Okay, so the first carboxylic acid is one of the material or functional group that we use daily in our life. An example of that is the vinegar, which is acetic acid. I'm sure you use it daily in your daily life. Acetic acid. Also sodium citrate. This is the type of salt that that is used to give the sour taste, mainly in chips. They are used, sodium citrate, in some salad dressing. There are also sodium citrate. Any kind of food that we consume that it has a little bit of a sour taste, that's sodium citrate. Usually they don't write it as sodium citrate. It's given E331 as the name in the names of the material that we consume. Monosodium glutamate, you might know it, especially if you're a food or a nutrition major, as MSG. So usually this gives intensify the meat flavor. So for example, in a barbecue chips, they use MSG. So the first thing that we're gonna do, as usual, is teach you how to name them, how to prepare them, and the reactions. This is how we're gonna go in this one. So, how to name them? The longest chain that contains the carbon of the C double bond OOH. Definitely that C double bond OOH or the carbon of the carboxylic acid should be given carbon number 1. The longest chain, the substituent the lowest number possible. Cross the E at the end of the name, replace it by oic acid. So for example, if it is 2 carbons, something like this. So the longest chain 1, 2, that's mean it is ethane. I'm gonna cross the E at the end, replace it by oic acid. So this is ethanoic acid. You know this better as acetic acid or vinegar. So the common name of this is acetic acid, which is the vinegar that you use. Should I put 1 ethanoic acid? Do I have to tell where exactly is the C double bond OOH? No. Because it must be carbon number 1. Because if I move it 1 carbon, it's not gonna be OH from one side and an R from the other side. So when naming carboxylic acid, there is no need to tell exactly where is the carboxylic acid. It must be carbon number 1. So what I'm gonna do next is as simple as that. So go ahead, name these 2. Hexanoic acid, very good. The longest chain. 1, 2, 3, 4, 5, 6. It's hexane. I'm gonna cross the E, replace it by oic acid. So it's hexanoic. And intentionally and definitely there is a space between the 2. So this is a space in there. We don't put hexanoic acid as one word. There is a space between the 2. What about the second one there? The second compound in the slide. What is the name of that? Very good. 3-methylbutanoic acid. Always a dash between a number and a letter. A comma between a number and a number. So 3-methyl butanoic space acid. Okay, which is, first of all, is carboxylic acid acid, base, or neutral in pH? It's carboxylic acid. Okay, it must be an acid. So is carboxylic acid as acidic as HCl? No, they are weak acids. Carboxylic acids are weak acids. So now let's see which compound is the most acidic out of all of these. And the reason that I'm asking you directly, because I think based on your experience in this class, you should be able to answer this question. Anytime before this lecture, I asked you to tell me which is more acidic, what was the first thing that you should do? Very good. Draw the conjugate base. And the most popular answer is A. A is the right. This is the conjugate base of the first one. This is the conjugate base of the second one. This is the conjugate base of C. So in all three of them, the minus is on an oxygen. So I can't say, oh, the minus is on a carbon, the other on an oxygen, and talking about electronegativity. All of them, the minus is on an oxygen. Now, by taking another look, I can see that in the ethoxide, which is the conjugate base of ethanol, there is no resonance structure. It's just this compound, the minus charge is localized on the oxygen. Comparing it to this, I can see that there is a resonance structure in there, and the same in here, there is a resonance structure. So at least I ruled out that C couldn't be the most acidic because it does not have its conjugate base, does not have a resonance structure. Now between B and C, I can see that both conjugate base of B and C each has a resonance structure. So they are almost equivalent from that point of view. But looking at the conjugate base of A, I can see that there are 3 fluorines connected, that they are the neighboring on the alpha carbon of the COO minus. And we know that fluorine is the most electronegative element of all the periodic table. So it is definitely a strong withdrawing group by inductive effect. So having 3 withdrawing groups next to that COO minus, in addition to the resonance, it's kind of diffusing the electron density. So that's make it more stable. So this is the most stable conjugate base, which makes this the most acidic. Now I'm just going to comment on this. We know that the methyl or alkyls in general from chapter 16, that they are donating by inductive effect. So this is intensifying the charge. So comparing conjugate base B to conjugate base A has a withdrawing group that is stabilizing the conjugate base, while B has a donating group which is intensifying the charge, making it less stable. And I'm always referring relative to the conjugate base of A. So from now on, if I give you any acid, any aliphatic acid, that means it's not directly connected to a benzene ring, you just draw the conjugate base, figure out which is more stable. The one that is more stable is the more acidic. From this in here, you can also conclude that alcohols are definitely less acidic than carboxylic acid, because anytime you have an alcohol, you're not going to have a resonance structure, as it is the case right here. Does this make sense to you guys? So it should be now common knowledge for you from now on that alcohols are less acidic than carboxylic acid. Okay, just to prove it to you, here is the table for the by pKa. So if I'm comparing ethanol, the pKa of ethanol, which we just seen in that example, it has pKa of 16, while the trifluoroethanoic acid, which is A in the slide before, has a pKa of 0.23. So definitely alcohols are much less acidic than all the other carboxylic acid. Now, as you can see also that phenol, if I compare the pKa of phenol to ethanol, there is a big difference. Let's see more example and see how you're going to handle it. Very good, C is the right answer. So, as usual, I'm going to draw the conjugate base. of each. So we can easily rule out A, because in A it's a phenol, this is the conjugate base of a phenol. One thing about it, yes, the lone pair is on the oxygen, yes, it has resonance with the benzene ring, but if I compare it to the other three, this has a resonance with this. In addition, that the benzene ring itself has a resonance, is the double bond in the benzene ring is one single bond with the is one single bond from the C double bond of the oxygen in there. Add to that this O minus is close to a withdrawing group in each one of these. So definitely A is the least acidic because of all the resonance structure in B, C, and D. Now comparing B, C, and D, I can see that the difference in there is a substituent on the para. What do you know about NO2? Is it a withdrawing or a donating group? Go back to chapter 16 reactivity chart. It's withdrawing by inductive effect. And what about the methyl in here? Donating. So I have a donating group and I have a withdrawing group. Which would stabilize the COO minus? A group that is withdrawing the charge, making things more stable, or a group that is intensifying the charge? The one that is withdrawing. So this is most stable because you have a withdrawing group in there. So if I ask you to conclude for benzoic acid, which is the most acidic benzoic acid out there? The one with a deactivating group on it or an activating group? Deactivating group. It's the opposite of the reactivity of a benzene ring. So deactivating groups group on benzoic acid makes it more acidic. So just put a note in there that it's exactly the opposite of reactivity of benzene ring. So if I have a benzoic, but I have to have benzoic acid because it's a source of H+. So if I have couple of different benzoic acids, the one that has the most deactivating group is the one that is more acidic. Why? Because we know most deactivating groups are withdrawing, or all of them are withdrawing, either by resonance or inductive effect, which gonna stabilize the benzene ring, which make the conjugate base more stable. That means more acidic. And this is what you're gonna see in the next slide. As you can see, this is how the pKa range based on the fact of deactivating or activating group. You can see as the more deactivating the group, the pKa is lower. OH, which is one of the most activating group, the pKa is 4.48. Definitely all of them are more acidic than a phenol, more acidic than the non-aliphatic alcohol. So what do you think? Do you think alcohols are more acidic or less acidic than benzoic acid? Definitely less acidic than benzoic acid. So it's still, alcohols are less acidic than phenol, and I mean by alcohol, aliphatic alcohols are less acidic than phenol. Phenol is less acidic than benzoic acids and all its other stuff. Then you have the carboxylic acids that they are, for example, they have a withdrawing group on the alpha carbon. Does the trend make sense to you guys? Cool. So as you can see, benzoic acid is in between. So if I just have benzoic acid by itself, it's in between those with an activating group and those in acidity between the two. So if I ask you to rank them, definitely the benzoic acid is in between the two, is in between 1 with the activating group and one with a withdrawing group or deactivating. Okay, here how to prepare carboxylic acid. For both of these reactions, we already talked about in chapter 19. So this is just a revision. How can I take an aldehyde to carboxylic acid? Okay, let's start with the easy one. How to take primary alcohol to carboxylic acid. KMnO4, chromium trioxide H+, or sodium dichromate H+. So this is one method to prepare carboxylic acid. The same, I can use chromium trioxide H+, chromium trioxide H+, or sodium dichromate H+, to go from an aldehyde to carboxylic acid. Let's see the other method to prepare that, to prepare carboxylic acid. So this is a new method. We never discussed this method before. So if I have Grignard reagent, which we usually prepare from Rx, adding to it magnesium to get to the Grignard reagent, is there any limitation of the Rx that I use with Grignard? No limitation. It can be primary, secondary, tertiary, benzene, vinyl, whatever. So no limitation for what I use as Rx in Grignard reagent, which make it one of the most broad methods because I can prepare whatever I want. So after preparing the Grignard, if I add CO2 as a first step, CO2, the CO2 gas that you know, followed by H3O+, I'm going to end up with this carboxylic acid. So here is the RMgX, and I'm adding CO2 to that. This is the Lewis structure of CO2. My guess it looks familiar, right? It's a C double bond O, which this is electrophilic. Guess what? It's more electrophilic. It has two C double bond O. So as we've seen before, the Grignard being Grignard, being a nucleophile, it's gonna attack the carbon of the carbonyl. My guess all of you knows what's gonna happen next. So it's not very different than what you've seen before. Definitely with the MgX in the solution, counter-ioning this, the magnesium playing the role of a counter-ion. Then the next step is H3O+, which all of you know what's going to happen. It's a base. This is the conjugate base of an acid. And it's going to pick the proton. Here we go. This is the prep of carboxylic acid. R can be anything. It can be benzene. I can start with any alkyl halide I want and end up with the carboxylic acid. But we also talked about one method in chapter 19 that I can end up with carboxylic acid, or RC triple bond, and I can hydrolyze that to carboxylic acid. And this is the third method, the fourth method to prepare carboxylic acid. So if I have an Rx and I add to that nitrile, so I'm starting with an alkyl halide. This is R triple bond CN. So I end up with the nitrile. Before I go any further in here, is there a limitation for the alkyl halide that I'm using in here? Can I use tertiary? Rx, not tertiary. Can I use benzene? Can I use this to be benzene and the cyanide attacking the benzene? No. Can I use this to be... Can Rx be this? Vinyl? No. So this is the limitation. As you can see, Grignard, no limitation. We come to the nitrile, it couldn't be tertiary. It can't be vinyl, it can be phenyl. So I'm slightly limited to primary, secondary alkyl halides for this one. Now, what is the other thing that you recognize doing this? That if I start with a certain alkyl halide, I'm adding 1 carbon to it, right? So if I start with 2 carbons in here, I'm adding 1 carbon to that. What about the Grignard? Did I add 1 carbon to that? Let's go revisit that. In here, did we add 1 carbon? Yes. So the Grignard method, there is the addition of 1 carbon from the alkyl halide. And in the case of nitrile, I'm adding also 1 carbon. What about the oxidation of a primary alcohol? No change on the number of carbons. What about the oxidation of aldehyde? No change in the carbons. So in other words, what I'm trying to tell you, that if you're given starting material, end material, if the number of carbon changes by 1 carbon, then your choice is either Grignard or nitrile. If there is no change on the number of carbons, then you're starting with an alcohol or aldehyde. Does that make sense to you guys? This will narrow it down for you when you're doing reactions. Okay, the next step is the hydrolysis of this, which we learned it's either by adding H3O plus heat or OH minus heat. So either acidic or basic conditions. So this can be either NH3 or ammonium. It depends whether you did the acidic condition or basic condition. So for the basic condition, you end up with ammonia, NH3. With acidic condition, you end up with ammonium. Right? What is the major product of each one? Let's start with the first one. Let's start with the basic. Is there a reaction? No reaction. Why? Because I have a nitrile or cyanide and nucleophilic attack on a benzene or vinyl or tertiary, it's not going to work. No reaction. So mainly I'm showing you the limitation in an example. What about the second one? And I mean the second reaction in the slide. Would it work? Let's start with the basic. Would we have a reaction? Yes. What would be the product? Benzoic acid. Very good. So the first step, this forming Grignard reagent, this attacking that. So 1 carbon more, and this is the benzoic acid. Now this is my question for you. Show me another method to prepare benzoic acid. It could be from any chapter from the start of the semester till now. KMNO4. So what is the requirement for that? Very good. I need at least 1 benzoic hydrogen. It could be whatever. All what I need is at least 1 benzoic hydrogen. Benzylic hydrogen, not benzoic. Benzylic hydrogen. And if I add KMNO4, H plus or heat, that will end me up with the benzoic acid. So in other words, there are other methods to prepare benzoic acid. But cyanide is not one of them. Okay, here is the map of the prep of carboxylic acid. Please take 1 minute and fill out this chart. And this is just to help you to put all the different ways of preparing carboxylic acid on one map. And please write the limitations of the reaction if there is any. So I'm going to start right here. So changing of alcohol to carboxylic acid or preparing carboxylic acid from an alcohol. Is there a requirement? Can any alcohol be changed to a carboxylic acid? Can a tertiary alcohol be changed into carboxylic acid? No. Can a secondary one? Secondary will go to a ketone. So if I have a secondary alcohol, I add chromium trioxide H+, I'll end up with a ketone. So that alcohol must be primary alcohol. If I add chromium trioxide H+, or sodium dichromate H+, I'll end up with a carboxylic acid. Aldehyde to carboxylic acid. There is no limitation. Any aldehyde can do so. The reagent is exactly the same as that of a primary alcohol to carboxylic acid. Going from nitrile to carboxylic acid, it's a hydrolysis reaction, either by adding H3O plus heat or OH minus aqueous heat. But to prepare the nitrile, I should start with an alkyl halide with Cn minus. What are the limitations in here? Not tertiary, not phenyl, not vinyl. So I'm putting all the limitations in the same slide so that when I'm looking at the summary and doing the OWL, I have all the reactions with the limitations in here. So Grignard, CO2, H3O plus, I can get to a carboxylic acid with one more carbon than the Grignard itself. I can prepare the Grignard from Rx with Mg. Is there a limitation? Is there a limitation? What should be the Rx when I'm using Grignard? Could be anything. Now, benzene to carboxylic acid, it's more specific. I mean that from benzene to benzoic acid, I can do that by Grignard. So, taking this to the Br, add to that magnesium as a first step, CO2 as a second step, and H3O plus as a third. I can start with the benzene, do Friedel-Crafts alkylation to have at least one benzylic carbon, then KMNO4, H plus, it goes to the benzoic acid. So mainly I'm repeating the slide before, guys, okay? So it's KMNO4 for any alkyl as long as the benzylic carbon has at least one benzylic hydrogen. Carboxylic acid, one of the most important reactions of carboxylic acid is going from carboxylic acid to acid chloride. Where did you see acid chloride before? Where did we use it? Very good, Friedel-Crafts acylation. So we can prepare that acid chloride from carboxylic acid. And the way that we do that is using SOCl2 80 Celsius. And sometimes even at room temperature it would take place, but it will be slightly slower, but the reaction will take place even at room temperature. Okay, now what is the product of these two steps? Okay, let's start with the first step. So the first step in here is KMNO4. So there is at least one benzylic hydrogen. So I'm taking this to the benzoic acid, followed by SOCl2. That is the reaction of carboxylic acid to an acid chloride. So I can prepare this acid chloride starting from, yes. First, is this an oxidation reaction or reduction reaction? Reduction. So what is or are the reducing agents that we use? Okay, so we agreed that this is a reduction reaction. So what are the common reducing agents that we used in this course? Okay, sodium borohydride or lithium aluminum hydride. So would sodium borohydride, according to your knowledge from chapter 19, would it reduce carboxylic acid? No. So lithium aluminum hydride is the one that's gonna reduce carboxylic acid or esters into primary alcohol. So sodium not I'm gonna write it in here so that when you're doing revision for the exam, you kind of have it written. Not sodium borohydride. It's not strong enough to reduce the carboxylic acid into a primary alcohol. You need lithium aluminum hydride. This is a new reaction. We call this esterification, and we give it the name Fischer esterification, named after the scientist who figured it out. Those who are in the chem2 in the lab, either you already done that experiment, the esterification experiment, or you will do it sometime this week or next week. Esterification, just let's do a quick revision. What is an ester? So this is the generic formula of an ester. It's R C double bond O and an O R prime from the other side. The R's can be the same or different, but this is the ester. Now, esters is one, at least for me, is one of the great chemicals. They are, most of the esters have a very nice smell, like the smell of the jasmine is because of this ester in here. We're gonna learn how to name them in the next chapter, so don't worry about the IUPAC naming of these esters. The strawberry is also, the smell of the strawberry is because of an ester. Any other kind of the pineapple, you can keep going, the banana, and the banana smell is also because of an ester. So in any, if you're eating any or drinking any of those drinks that they have banana flavor, pineapple flavor, if you look at it, you're gonna see O8 in the name or 8 in the name, because those are the esters that are giving those flavor. Usually when they tell you it is artificially flavored, that means that ester is prepared in the lab and they put it inside your drink, and this is how it smells and tastes like banana or pineapple. So we can prepare esters, the first method under acidic condition, by using carboxylic acid and alcohol. And I'm going to keep the color code so that you see where each is coming from. So if you look at the way that I've wrote the product, this part is coming from the carboxylic acid, and this part of the ester is coming from the alcohol. So I'm adding carboxylic acid to an alcohol to end up with the ester. As you can see that the reaction is in equilibrium. So what you're going to do if you want more of the ester formed? Let's say we are in a lab setting and I ask you to do whatever you can to get the highest yield of ester possible. What you're going to do? Add more alcohol or carboxylic acid, more of the starting material. It depends on the price. If the alcohol is cheaper, I'll add more of the alcohol. If the carboxylic acid is the cheaper, between the two, I'll add more of the carboxylic acid. Remove the product from the flask, and you're gonna do that in the lab. If you are part of the Orgo lab, you're gonna be doing distillation of the ester as you're doing the reaction. This is why you do distillation as you're doing the reflux, so that if there is an equilibrium reaction, or most of the time you do that when there is an equilibrium, to push the equilibrium toward forming more of the product. Okay. Great job. So mainly this is Fischer esterification. The easiest way to map it back, this part is coming from the acid. So this is the acid. This part in here, which is ROH, is coming from the alcohol. So the right combination, there is no other combination in a Fischer esterification, but this is the carboxylic acid, benzoic acid is the carboxylic acid, and methanol is the alcohol that I'm using in this one. So I can also prepare esterification in the following method. So the first thing is I have a carboxylic acid, which is the same as the Fischer esterification. I have carboxylic acid. In this case, I add sodium hydroxide or potassium hydroxide or OH minus to the carboxylic acid. And that, what do you think would be the result of this reaction? I'm adding a carboxylic acid to an AOH. It's an acid-base reaction. I'm adding an acid to a base. So what's going to happen is going to the conjugate base of the acid, and this is the counter ion. So the role of this is just to balance the charge, plus water molecule formation. Now, this one in here is a base, but at the same time a nucleophile. Most bases are good nucleophile. So what I add to that next, I'm adding R prime I, and just to keep it general, instead of R prime I, it's R prime X, where X can be BRI chlorine. So it's not limited to I, okay? So it's just to be more kind of in general, talking in general. What do you think gonna happen next? She's saying it's a very typical nucleophilic substitution in which the nucleophile will attack this, the I or the X in general will leave, and the result of that is R, C double bond O, O, R prime. Look at it. What is this functional group that I ended up with? It's an ester. So in here, I'm starting either with a conjugate base of an acid or with an acid doing acid-base reaction, then substitution reaction. Now, from your experience in this class, what should be the limitation of this reaction? Without me telling you, you should by this point know that. Perfect. No tertiary. No phenyl halide. No vinyl halide. So as you can see, whenever I have a substitution reaction and there is a nucleophilic attack on an Rx, the R prime X, not tertiary, not phenyl, and not vinyl. So the reason that I asked you before telling you the limitation, I'm trying to tell you at this stage of the course, you should be able to judge it yourself without even memorizing. It's a substitution reaction. I'm sure that it couldn't be benzene, vinyl, or tertiary. Okay, so if I have this dicarboxylic acid, and what I mean by dicarboxylic acid, two carboxylic acid in the same compound, I add heat plus H plus to that. I'll end up with this. We call this reaction decarboxylation. From the name, it's removal of CO2 from that compound. The requirement for this reaction to happen, I need two carboxylic acid in the same compound, and they should be beta from each other. So this is the alpha carbon of this carboxylic acid. This is on the beta of it. You can think about it the other way around, thinking this is the carboxylic acid, this is the alpha of this carboxylic acid, this is the beta carbon of it. So they are beta from each other. So those dicarboxylic acid, they are beta from each other. Does the reaction make sense to you? Me personally, it wouldn't make sense to me just by seeing it. I need a mechanism. I'm going to show you the mechanism. You're not responsible for this mechanism in the sense I'm not going to ask you to show me the mechanism, but I think it's very hard to see how did we lose CO2 in this without seeing the mechanism. And the reason that I rotated the molecule just because it's easier to see what's going to happen in there. So you can see this mechanism in two ways. Either the lone pair of the oxygen are the one that attacking, or this double bond. Either or, it's exactly the same result. So this is picking the proton in here, the hydrogen on the neighboring, on the beta carbon. The hydrogen now is giving its electron to this. Now these are ending up on this carbon. I'm going to call them A, B, C as carbons so that you can see it. Or this sometimes written in this way, either or, it's the resonance structure. So after a couple of steps in here, this will end up being COOH, and this will pick up proton to be CH3. So you can think about it as this hydrogen being picked, and this carboanion gaining a proton in there. And this is how you end up with a product in there. So this mechanism, all these arrows happens at the same time. Now, if I want to map it, if I don't want to remember the mechanism, I want to map it. If I have two carboxylic acids, they are beta from each other. One of them will survive, the other will leave as CO2. So, the way, first of all, you need to make sure that the requirement is there. Two carboxylic acid, they are beta positioned from each other. And then what's going to happen, one of them, we're going to lose one of them, either or, it doesn't matter, as CO2. And whatever left, which I'm going to circle in here, is going to be the carboxylic acid. Make sure to count the number of carbons, because as you can see, the only difference between all these choices is the number of carbons. So 1, 2, 3, 4 carbons and the benzene. 1, 2, 3, 4 carbons and the benzene ring, which make A the right answer. Okay? Okay, so this is the other reaction that only dicarboxylic acid beta from each other will undergo this reaction, not all carboxylic acid. So for just monocarboxylic acid, for me to decarboxylize it, I need about 250 to 400 degrees Celsius. At that point, the carboxylic acid itself, it will burn into CO2 and water. This is why this is only can happen for dicarboxylic acid at a reasonable temperature, for it to happen without disintegrating the compound as a whole. Enjoy your day, and I'll see you tomorrow in class.